what is a cooling tower? It's a good question. A lot of times when I'm talking with people, they say it's a cooling tower. It's just a box that makes water moderately colder. So going from 95 degrees to 85 degrees. Very true. Simple idea, big box that makes water cold. But it's, as Clint said, very vital to our everyday lives. Cooling towers are at hospitals, they're at army bases, they're at pharmaceutical industries, food industries. They cool hotels and office buildings. They're in all sorts of different applications in our world that we take for granted today. So understanding them as we are working with them, installing them, designing them can really enhance our experience with it. So simply put, a cooling tower is just a heat exchanger. All you're trying to do is remove the heat from your chiller in an HVAC system. And so that's what it's doing. It's pulling your process fluid into the cooling tower, trying to evaporate some of that water, which is where you get a lot of that cooling. And I'll dive into that a little bit more. So you're just going to be exchanging where that heat is. Typically, when you're evaporating that water, rule of thumb is going to be about 1% of your design flow rate going through your cooling tower. Maybe a little less, but quick calculation is about 1%. So how does a cooling tower work? A couple standard components of a cooling tower. Obviously, you're going to need water. You're also going to need air. Ways to kind of create that air, you can kind of see you have a fan that's going to be pulling air through a cooling tower. You also have this heat transfer media, we call it fill. And so that fill is going to try and spread that water as thin as possible so you get as much air and water interaction, which will create that evaporation and that cooling. So again, simple process, but specific design, and it's designed to do it as efficiently as possible. So in the cooling process, there's a couple different types of cooling that happen. So there's sensible cooling. You can think about this like the radiator in your car or the HVAC system outside of your house. It's a indirect cooling, so air is going to be cooling the fins and the coil, and then inside that coils you're going to be your fluid, and then that coil is cooling that fluid. Now that's a sensible type of heat, and so that's going to be driven by your dry bulb temperature. And so with that, typically you're going to be seeing that the cooling is going to be about 1 BTU whenever you cool 1 pound of water 1 degree Fahrenheit. And take that in contrast with the next type, latent cooling. So this is going to be an evaporative type of cooling. And so if you take that same 1 pound of water and instead of just cooling at 1 degree, you actually evaporate it, you're going to be removing 1,000 BTUs. So it's much more efficient from a cooling standpoint. Driven by the wet bulb temperature instead of the dry bulb. And so it's important to understand what that wet bulb temperature is. So if you're watching your weather channel at night and the anchorman says, our dew point is 78 degrees, that dew point is your wet bulb temperature. So simply put, it's the lowest temperature achievable through evaporative at a given ambient temperature and a relative humidity. So really in evaporative cooling, it's kind of your limiting factor. You can't cool that water below what your wet bulb temperature is. You can think about trying to put a beer in a fridge and cooling it down to 38 degrees. But if your fridge is at 42 degrees, you can't cool that beer down to a 38 degree temperature. So it's your limiting factor. So it's very important. And we'll talk about it a little bit later as well. So understanding, if we're going to be talking a little bit or mostly about HVAC systems today. So understanding what a refrigeration ton is and kind of its history can be fun and important as well. So talking about the history of the refrigeration ton, back in the day, you used to have ice plants, and those ice plants would kind of get measured in how many tons of ice they would produce in a day. So converting 2,000 pounds of 32 degree temperature water to 2,000 pounds of ice. So when you take that 2,000 pounds, add the heat of fusion, 144 BTUs per hour over the course of 24 hours, you get your 12,000 BTUs per hour. and that's what our refrigeration ton is today. So it's important to understand that that's what you're looking at whenever you're looking at a chiller. Now, whenever you dive into the cooling tower world, it goes beyond the chiller. So in an HVAC system, you're going to have your heating load over there on your evaporator side of your chiller. Now, in a chiller, you're also going to have a compressor. And in that compressor, you're going to be adding a heat of compression. Kind of CTI standard is about 3,000 BTUs. And so once it goes through there and into the condenser, the water that the cooling tower is seeing is going to be that 12,000 BTUs from your load plus 3,000 BTUs from that heat of compression. So it's actually 15,000 BTUs nominally that the cooling tower is going to see. So a cooling tower ton is about 15,000 BTUs. So, as you're designing your system, say maybe you have a 500-ton chiller and you want someone to design for it, you got to understand that the tower is actually going to see a larger heat load than that 500 tons. Now, that 3,000 BTUs, that was kind of nominal. Chillers have gotten much more efficient. So in today's world, it might not be 3,000 BTUs for that heat of compression. It might be closer to 1,500 BTUs for that heat of compression. And so that, if you designed it that way, if you designed with 3,000 BTUs in mind, you might be a little bit oversized on the cooling tower side, which might not be a bad thing, but it's good to understand. And then on the flip side, if you get maybe into a more industrial side of the world, you have maybe a gas-fired absorber, and the total might be a little over 22,000 BTUs. Or steam-fired, you can get much more BTUs that you're going to have to reject if you're in those kind of applications. Or if you're getting into water source heat pumps, and you might want to be using a fluid cooler instead, which we'll dive into a little bit. So it can kind of get confusing, how much is my heat of compression on my chiller versus another chiller? What do I need to design for? And I want to talk about, there's 4 pieces of information that if you give, we'll be able to design things perfectly to meet your specific requirements. So if you give us our flow rate, that's leaving the chiller, the hot water temperature that's leaving the chiller, the cold water temperature that you want coming back to the chiller, and then your wet bulb temperature, which again, that's your environment, your dew point. If you give us those 4 things, we're going to be able to design a cooling tower that will meet your needs.
Stephen, I have a question.
Yes.
What's the best range in between hot water and cold water entering the tower?
So kind of standard in the HVAC.
Totally loaded question, by the way.
Totally loaded question. Typically for an HVAC system, you're going to see 95-degree hot water, 85-degree cold water. So it's going to be a 10-degree range. So that difference between your hot and cold water temperature is considered your range. That can vary depending on what your chiller requirements are. So there are some chillers out there that operate more efficiently, where they get a colder water coming back to them. Mm-hmm. We'll talk about this a little bit later, but you can actually oversize your tower a little bit to cool that water more to help your chiller operate more efficiently. It can save you energy. And if you design this whole thing up front, you can actually get a smaller chiller and save a lot more upfront capital cost as well.
Great. Thank you.
Yep. Another term that we're going to talk about here is our approach. And that's the difference between your cold water temperature and your wet bulb temperature. Kind of going back to our beer in the refrigerator example. You won't be able to get colder water than your wet bulb temperature. So things to kind of keep in mind. And then going through some rules of thumb, and just like as you're looking at things and designing your tower, just some quick ways to look at it. Obviously, this is an oversimplified graph. As your heat load goes up, your tower size goes up. But that can look different. So, in a cooling tower, if you make it larger, you're going to have a larger amount of heat transfer surface. So that's one way that a tower could get bigger. Or you could keep the same amount of heat transfer surface, same size, but increase your horsepower. So you're pulling more CFM through that and still getting the same amount of cooling. So the way that the size factor changes can vary some, but as you add heat load, your tower is going to have to reject more heat, and thus it might get bigger or higher horsepower. Now kind of looking at your approach, remember, it's the difference between your cold water temperature and your wet bulb temperature and your tower size. So typically in an HVAC system, you might see that 7-degree approach coming up here, and you see it's like a 2.0 tower size factor. You might want to jump down to a 5. I've seen 5-degree approaches pretty common as well. And you can see that the tower gets bigger. So that tighter that approach, the tighter you're trying to get to that absolute coldest temperature that the wet bulb will allow you to get, the tower is going to have to work harder and get bigger. I will make a note. CTI, they're the Cooling Tower Institute. They're the ones that come in and test all the manufacturers' cooling towers to make sure that they are performing thermally how they say that they are. They will not certify a tower below 5-degree approach. And that's just out in the world. It's really hard to be able to measure that specifically. Now, manufacturers, they know how their towers work. They can do studies and do tests and guarantee the performance of their towers, but it won't be CTI certified if it's less than a 5-degree approach. And something else I kind of want to touch on because it's counterintuitive. A lot of times whenever you're out sizing your tower, you just think whenever it's colder outside, it's going to be a lot easier for the cooling tower to reject that heat. But that's not actually the case. So in this example, you have a wet bulb temperature and cold water. And if you're looking at it, say you have a 78-degree wet bulb temperature, you come up here and you're at an 84-degree cold water. So that's a 6-degree approach. And then you follow that same line down and you get to, let's say, about a 79-degree cold water, and be at a 72-degree approach. And so that's going to be a 70-degree approach. So you can see that the approach gets larger the colder it is. And that's because the air isn't able to absorb water as effectively in colder temperatures. So you're not able to evaporate water and reject that heat as much in colder temperatures. So something to kind of keep in mind as you're designing your tower. And again, on the wet bulb temperature, the wet bulb is what's driving the evaporation, not the dry bulb. So ASHRAE handbook, they've gone all around the world, they've collected data, and they know, there's the wet bulb temperature for a certain location over the course of a year. So typical engineering design, what you're going to do is you're going to design for a 0.4% design wet bulb. Now, when you're looking here, again, there's the wet bulb temperature here and the dry bulb temperature. Being an evaporative process, you want to make sure that you look at the wet bulb temperature and not the dry bulb. So here, or up in Charlotte, North Carolina, the design wet bulb 0.4% is a 77.3 degree wet bulb temperature. Now, what does that 0.4% mean? Look over here. So basically it's saying 0.4% of the year, or 35 hours out of the year, your wet bulb temperature will be at or below 77.3 degrees. So if you're designing your cooling tower for that 77.3 degrees at a 0.4% design wet bulb, it means that 35 hours out of the year, that cooling tower might not be meeting its design duty. But the rest of the year, it could be oversized as well, because in cooler weather, that wet bulb temperature will be lower. And kind of leading into this energy saving standpoint, if you have a VFD that's able to ramp that fan speed up and down, you'll be able to take advantage of the parts of the year where the wet bulb temperature is lower than that design wet bulb. Or maybe you have an application where in the summertime, when it is the hottest, there won't be as many occupants in a building, or you won't need to cool it as much. You could design for a 1% wet bulb, and that'd be a 76.2. So 88 hours out of the year, the tower might be not meeting that thermal design duty. But again, the rest of the year it'd be oversized, and you'd be able to save energy by ramping those fans down. So typically in this area, we'll see it designed at a 78-degree wet bulb, which is a little bit higher than the 0.4%. That's just kind of what I've seen out in the industry for the most part, and it works pretty well.
So we have a question that came in.
Yeah.
Going back to that last slide, So what happens with the cooling tower during those 35 hours of the year? Is it just not, is the delta T just not?
So the cold water temperature of the water would actually rise slightly. So then the your chiller wouldn't be either operating quite as efficiently or producing quite as cool of air in your building. So say that you have a school or a gymnasium or something like that, and they're not using the gym in the middle of the summer, school's out. Maybe they don't mind if the temperature gets up to 75 degrees instead of 72, something like that.
Thank you.
Mm-hmm.